Monitoring isn't knowing about when something breaks, it's knowing about when something meaningful breaks. Because if every fluctuation becomes an emergency, nothing is. We're engineering signal, reducing noise, designing urgency, and building monitoring systems people actually trust. This is advanced alert engineering. On the screen is what flapping looks like. The system detects downtime, then it recovers, then it fails again, then it recovers again. And if your alert routing is aggressive, every one of these transitions becomes more noise in Slack, email, SMS, or whatever else you use. Now here's the key point. Flapping is not StatusCake being weird. Flapping is a mismatch between sensitivity and stability. This is the relationship. If your configuration is more sensitive than your environment is stable, you enter the flapping zone. And that zone is created by common causes. Timeout set too low, so slow responses become down. Confirmation too low, so one bad node becomes an incident. Check rate too high, so you sample instability too frequently. Regional routing variance, CDN behavior, and firewall edge cases. The system isn't broken, it's doing exactly what you asked it to do. It's detecting variability. The problem is, you configured variability to equal outage. There are 3 levers that stabilize monitoring without turning it off. First, confirmation servers. This increases confidence. Second, timeout. This increases tolerance to slow responses. Third, alert delay. This reduces human interruption for short disruptions. Now the important distinction. Stabilizing does not mean ignoring outages. It means filtering instability so only meaningful failure escalates. That's how you reduce flapping while still detecting real incidents quickly. Here's the mental model for flapping. Flapping happens when you configure monitoring to be more sensitive than the system can consistently satisfy. To fix flapping, you don't hope it stops. You rebalance confidence and tolerance. Now that we've stabilized single signal reliability, we can go one layer deeper. Because the next question is, how do we validate outages across geography? Monitoring from one location gives you one perspective. Monitoring from multiple locations gives you a distributed verdict. Here's where the quorum logic matters. Because a failure from one region doesn't automatically mean the site is down globally. Let's break it down properly. On the left, single region. If that region fails, you get downtime, fast, simple, but vulnerable to regional bias. On the right, multi-region. Now you're asking, is this failure consistent across geography? Is this quorum thinking? If one region fails, but 2 others pass, that's often routing noise. If multiple regions confirm failure, that's a stronger signal. So multi-location monitoring isn't just more checks, it's a reliability model. This is what global quorum really means. Multiple monitoring nodes test the same origin. Some pass, some fail. Majority confirmation produces the decision. Now the key benefit, it reduces false positives caused by single ISP issues, local DNS problems, transient routing, regional packet loss. But it comes with a warning. Multi-region can introduce noise if your application behaves differently by geography. So you don't pick global regions because it looks impressive. You pick them because it matches user reality. Now here's the part most people don't understand. During healthy operation, checks are distributed randomly across your region pools. But once downtime is confirmed, the system clamps, meaning we keep testing from the failing region to track the incident consistently. That's not a bug, it's intentional. It prevents your incident timeline being distorted by regions that were never failing in the first place. Random during health, focused during incident. This is how you get a clean recovery signal. So the mental model for multi-location monitoring is this. Single region gives you speed. Multi-region gives you confidence. Clamp behavior gives you consistency. Now we move into the final layer, because even with perfect monitoring, you still need to decide what deserves urgency. That is business criticality. Not every endpoint deserves the same alerting strategy. If you alert on everything equally, you train your team to ignore alerts. And if you delay everything equally, you allow critical incidents to grow. So this is where alerts engineering becomes operational design. Let's break it down properly. On the screen, think of your system as tiers. At the top, revenue critical paths. checkout, payment, login, your core API. In the middle, core functionality, dashboards, key pages, workflows. At the bottom, low priority, marketing pages, non-critical endpoints, internal tools with low impact. Each tier needs a different balance of speed, confidence, and interruption. Here is the trade-off. Too sensitive creates noise. Too tolerant creates blindness. The goal is balance. And balance depends on what breaks when the endpoint fails. High business impact means fast detection and high confidence. Low business impact means less interruption and more filtering. Alerting is not a universal rule, it's a strategy. On the screen is a practical matrix. Revenue critical equals fast checks, high confirmation, low delay, wide regions. Core functionality equals moderate checks, solid confirmation, short delay, regions aligned to users. And then we have low priority, which is a lower frequency, minimal interruption, longer delay, and limited regions. These aren't commandments, they're starting profiles. You tune based on your environment, but the principle is fixed. You align alert design with business impact. Monitoring is infrastructure, alerting is policy, and engineering both is operational maturity. Flapping isn't random, noise isn't accidental, false confidence isn't harmless. Every alert system is a design decision. So engineer the signal, reduce the noise, and design alerting intentionally. Because when incidents happen, clarity is everything.